Phenylethanolamine, sometimes abbreviated PEOH, or beta-hydroxyphenethylamine, is a trace amine with a structure similar to those of other trace phenethylamines as well as the catecholamine neurotransmitters dopamine, norepinephrine, and epinephrine. As an organic compound, phenylethanolamine is a beta-hydroxylated phenethylamine that is also structurally related to a number of synthetic drugs in the substituted phenethylamine class. In common with these compounds, phenylethanolamine has strong cardiovascular activity and, under the name apophedrine, has been used as a drug to produce topical vasoconstriction. In appearance, phenylethanolamine is a white solid. Phenylethanolamine is perhaps best known in the field of bioscience as part of the enzyme name phenylethanolamine N-methyl transferase, referring to an enzyme which is responsible for the conversion of norepinephrine into epinephrine, as well as other related transformations. Occurrence. Phenylethanolamine has been found to occur naturally in several animal species, including humans. Chemistry. Synthesis. An early synthesis of phenylethanolamine was by the reduction of 2-nitro-1-phenylethanol. Other early syntheses are summarized in a paper by Hartung and Munch. A more recent synthesis, providing a better yield, is by the reduction of benzoyl cyanide using LiAlH4. Properties. Chemically, phenylethanolamine is an aromatic compound, an amine, and an alcohol. The amino group makes this compound a weak base, capable of reacting with acids to form salts. Two common salts of phenylethanolamine are the hydrochloride, C8H11NO-HCl, M, P, 212 degrees Celsius, and the sulfate, C8H11NO, 2, H2SO4, M, P, 239 to 240 degrees Celsius. The pKa of phenylethanolamine hydrochloride, at 25 degrees Celsius and at a concentration of 10 m, has been recorded as 8.90. The presence of the hydroxy group on the benzoic carbon of the phenylethanolamine molecule creates a chiral center, so the compound exists in the form of two enantiomers, D and L-phenylethanolamine, or as the racemic mixture, D-L-phenylethanolamine. The dextrorotatory isomer corresponds to the S configuration, and the levorotatory isomer to the R configuration. The data given at right is for the racemate. The synthesis of S phenylethanolamine from mandelic acid via mandelamide has been described. The physical constants reported in this paper are as follows: M, P, 55 to 57 degrees Celsius, alpha equals plus 47.9 degrees, C 2.4, in ethanol. Pharmacology. Early, classical pharmacological studies of phenylethanolamine were carried out by Tainter, who observed its effects after administering it to rabbits, cats and dogs. The drug produced a rapid rise in blood pressure when administered intravenously, but had little or no effect when given by any other route. Doses as high as 200 mg given subcutaneously to rabbits did not alter blood pressure, nor were there any effects when the drug was intubated into the stomach. In man, a total oral dose of 1 gram also produced no effects. Doses of 1 to 5 mg per kilogram intravenously caused no definite changes in respiration in cats or rabbits, and additional experiments showed that phenylethanolamine had no bronchodilatory properties in animals. There was a similar lack of effect when the drug was given subcutaneously to man. In vivo and in vitro experiments involving cat and rabbit intestinal smooth muscle showed that the drug produced relaxation and inhibition. A detailed examination of the mydriatic effect of phenylethanolamine led Tainter to conclude that this drug acted by direct stimulation of the radial dilator muscle in the eye. Shannon and co-workers confirmed and extended some of Tainter's studies. After administering phenylethanolamine to dogs intravenously, these investigators observed that 10 to 30 mg per kilogram of the drug increased pupil diameter, and decreased body temperature. A dose of 10 or 17.5 mg per kilogram decreased heart rate, but a 30 mg per kilogram dose caused it to increase. Other effects that were noted included profuse salivation and piloerection. Phenylethanolamine also produced behavioral effects such as stereotyped head movement, rapid eye movement, and repetitive tongue extrusion. These and other observations were suggested to be consistent with an action on alpha and beta adrenergic receptors. Research by Carpenet and coworkers showed that phenylethanolamine did not significantly stimulate lipolysis in cultured adipocytes, fat cells, from guinea pig or human. Moderate stimulation, intrinsic activities about half that of the reference standard, isoprenolone, was observed in adipocytes from rat or hamster. This lipolysis was inhibited completely by buprenolol, considered to be a non-selective beta blocker, CGP20712A, considered to be a selective beta-1 antagonist, and ICI 118551, considered to be a selective beta-2 antagonist, but not by Senior 59230A, considered to be a selective beta-3 antagonist, using a beta-2 adrenergic receptor preparation derived from transfected HEK293 cells. Leopakis and coworkers found that in wild-type receptors, racemic phenylethanolamine had ~1/400th the affinity of epinephrine, and ~1/7th the affinity of norepinephrine in competition experiments with 3H-CGP12177. The two enantiomers of phenylethanolamine were studied for their interaction with the human trace amine-associated receptor TAAR1 by a research group at Eli Lilly. From experiments with human TAAR1 expressed in Rg-alpha-SAVE 12-664 cells, Wainscott and coworkers observed that R-phenylethanolamine, referred to as R-beta-hydroxy-beta-phenylethylamine, had an ED50 of ~1800 nm, with an Emax of approximately 110%, whereas S+-phenylethanolamine, referred to as S+-beta-hydroxy-beta-phenylethylamine, had an ED50 of ~1720 nm, with an Emax of approximately 105%. In comparison, beta-phenethylamine itself had an ED50 of approximately 106 nm, with an Emax of approximately 100%. In other words, phenylethanolamine is a TAAR1 agonist and trace amine. Pharmacokinetics. The pharmacokinetics of phenylethanolamine, after intravenous administration to dogs, were studied by Shannon and coworkers, who found that the drug followed the two-compartment model, with T1/2 alpha 6.8 minutes and T1/2 beta 34.2 minutes. The plasma half-life of phenylethanolamine was therefore about 30 minutes. Biochemistry. Phenylethanolamine was found to be an excellent substrate for the enzyme phenylethanolamine N-methyltransferase (PNMT), first isolated from monkey adrenal glands by Julius Axelrod, which transformed it into N-methylphenylethanolamine. Subsequent studies by Rafferty and coworkers showed that substrate specificity of PNMT from bovine adrenal glands for the different enantiomers of phenylethanolamine was in the order R-, PEOH greater than R, S, racemic, PEOH greater than S+, PEOH. Toxicology. The minimum lethal dose (ml/d) upon subcutaneous administration to guinea pigs was approximately 1,000 mg per kilogram. The ml/d upon intravenous administration to rabbits was 25 to 30 mg per kilogram. In rats, the ml/d after intravenous administration was 140 mg per kilogram. See also: halostachine, list of controlled D-methamphetamine precursors. References.